We'll wait for a few minutes for others to join. Okay. So welcome everyone to week 9 lecture tutorial for the course Fluid Mechanics. I hope everyone is regular to the lecture videos and the assignments. So in the past week 8 tutorial, we have finished up with the topic of flow lines, that is streamlines, streak lines, path lines, and timeline. Today we'll start with a new topic, that is conservation of mass or continuity equation, which we said. All right, let me share my screen. I hope my screen is visible. All right. So let us start the topic, that is continuity equation. Continuity equation, or you can say conservation of mass equation. Okay. So as per this, what does it state that the mass of the system should always be conserved. Whatever mass enters into the system should be equal to whatever mass has left plus whatever mass has been stored. Okay, suppose I have a system like this. Okay, this is a closed system. So if some mass enters into the system, mass flow rate input is equal to nothing but whatever mass has been out, mass flow rate out, plus mass flow rate that is stored. Okay, so we can say that mass flow rate in is sum of mass flow rate out plus mass flow rate stored. Okay, that's a simple definition. So what is mass flow rate stored? Then that is the difference of mass flow rate out in minus mass flow rate out. Okay. So how we can define? So in Cartesian sense, we can say that in x, y, and z form. So we can derive the derivation for it. So each velocity field, always remember that each velocity field must satisfy its continuity equation. If the velocity field don't satisfy its continuity equation, then the velocity field is not valid for that flow. Or you can say that that flow is not possible. That flow is not possible. Okay. So let me write here. Each velocity field must satisfy its continuity equation if velocity field isn't satisfied it's satisfies its continuity equation, then the velocity field is not valid for the flow. No, or you can say that that flow is not possible. Okay. All right. So let us draw some streamlines first of all. Short, small diagram. Okay. And let's take a fluid particle under consideration. Okay. And suppose that its shape is in a form of parallelogram. So I'll make a zoom view. It's not that, it's a, so it's basically a zoom view I'll make of that fluid particle. Okay. So that I can define in the form of Cartesian coordinates. So here it is a closed system. And let me tell you once again that it's a closed system. And this is nothing but your control surface. Control surface. And this is your control volume. Okay. And these both are defined for the control flow systems. Okay. In thermodynamics, you will study this thing. And I've already taught in my previous course in the last semester. Okay, so let's draw a fluid element that's a parallel pipe kind of scenario. Okay, let's suppose this has a dimension of, this is dx, this is dy, and this is dz. Okay, so suppose from the x direction the fluid enters. Okay, so this is your mass flow rate in x direction. Okay, and also leaves the surface, also leaves this element. So that is mass flow rate in x direction. From Taylor expansion, you can write that dou m by dou x dx. Okay, this is from the Taylor's expansion. That is x plus dx. This is nothing but your mass flow rate of x plus dx. Okay. Similarly for y and z direction. For y direction, mass flow rate entered y, mass flow rate exited is mass flow rate y plus 2m y 2y dy, and that is nothing but your mass flow rate of y plus dy. Okay, similarly in the z direction, so it entered from the base, that is mass flow rate z, and exited through here, that is mass flow rate z plus 2m z by dz. dz is equal to mass flow rate of z plus dz. Okay, so this is your mass that is flowing in all three directions. Okay, and the whatever mass difference is equal to whatever mass that gets stored inside this fluid element. Okay, gets stored inside this fluid. That is your mass flow. So from the equation, what we can write that mass in minus mass out in mass flow rate out in x direction plus mass in minus mass flow rate out in y direction plus mass flow rate in minus mass flow rate out in z direction is nothing but your total mass that has been stored. Okay, that has been stored. So what is difference of this and this is nothing but this and this terms get cancelled out. All right, and you are only left with this term. Okay, so we can write, and similarly for the other three directions, so we can write in overall that is minus dou m x by dou x dx minus dou m dot y by dou y dy minus dou m dot z by dou z dz is equal to dou m by whatever mass has been stored with respect to time. Okay. Now how we can represent the mass flow rate? Generally, since mass flow rate is nothing but density into area into velocity. Okay. Density into area into velocity in particular direction. So we can write for the x direction above, it can be written as dou of rho. What is area in the x direction will be? If the mass is flowing in the x direction, what will be the area? So if the flow is in this direction, so area which it is crossing is this. Okay, so that is nothing but your dy into dz. This is your area, dy into dz. Okay, so for this it will be rho, area will be dy dz, and velocity is in x direction. Okay, by dou y, sorry, dou x dx. All right, correct. Then again, similarly for each direction, you can write dou by dou y rho. What will be area in the y direction? It will be dx dy v dy, sorry, dx dz. My bad. Dx dz dy and dou by dou y rho dx dy, and this is dz. dz is equal to dou m by dou t. So if you what you do, you can write again it as dou of dou x rho of dx dy dz. Each term has dx dy dz, dx dy dz, dx dy dz. So this cancels out. Okay. And this m mass flow rate can also be written as, cancels out from the right hand side, that is this mass flow rate can be written as the total rho into dx dy dz t. That is your total volume into the net velocity. Okay. So dou rho by dou t dv. So this is dv is nothing but your dx dy dz. So rho u minus dou by dou y rho v minus dou by dou z rho w. Okay. So I have not written here W, and that is nothing but equal to dou rho by dou t. If you take everything on right hand side and equate, so it is dou by dou x rho u plus dou by dou y rho v plus dou by dou z rho w plus dou rho by dou t is nothing but equal to 0. And this is your general conservation equation, mass conservation equation, or continuity equation, whatever kind of flow it is, either it's steady, unsteady, laminar, turbulent, viscous, non-viscous, uniform, non-uniform, or rotational, irrotational. We have already done this types of flow in the previous tutorial. Okay. So here the case forms, if the case, this is a general continuity equation. So let me write here. General continuity equation. Okay. Case 1. Suppose I'm saying it is a steady flow. So steady flow. If the flow is steady, that means my dou rho by dou t will be 0. That means my this term will be 0, right? So how will I write the equation? Therefore, my equation will be dou by dou x rho u plus dou by dou y rho v plus dou by dou z rho w equal to 0. This is for steady. If the flow is unsteady, then it won't be 0. So for the unsteady flow, so that means density as well as velocity both are function of space as well as time. That means density and velocity are function of x, y, z, and okay. So you can write derivative of each term you will do now, okay, through the chain rule. So from chain rule you will do the derivative for this term. So that will be, first take the density out, dou u by dou x, okay, then take the velocity out, dou rho by dou x. Similarly for y direction, rho dou v by dou y plus v dou rho by dou y plus w, sorry, rho dou w by dou z plus w dou rho by dou z plus dou rho by dou t. Last, okay. So this is your form. So take out this term, and this term common with the common element rho. So rho is taken out. Dou u by dou x, dou v by dou y, dou w by dou z. Okay, and remaining other terms, dou u dou rho by dou x plus v dou rho by dou y plus w dou rho by dou z plus d rho by dt. Okay, so now from the previous tutorial, if you observe this term, if you see u dou by dou x, similarly this term, u dou by dou x, v dou by dou y, w dou by dou z is nothing but del grad of del dot. Basically, it is nothing but u or vector v, we can say u dou by dou x, v dou by dou y, w dou by dou z can be written as v dot del. Okay. What is the grad operator? Since grad operator is nothing but it's a vector quantity, that is dou by dou x I cap dou by dou y, j cap, dou by dou z, k cap. Okay. And what is velocity vector? That is u I cap plus v j cap plus w k cap. Okay. So this term is nothing but written as divergence of del dot u. So rho of del dot u or del dot v, del dot v, and the other term is written as v dot del of rho plus dou rho by dou t is equal to 0. Is equal to 0. Okay. So here, if you observe that this hole is a convective part and this is a local part. We have seen both these terms in the last one. And what is this term? It is the total derivative of density. Total derivative of density. So you can write this as rho of divergence of V plus total derivative of density is equal to 0. And this is a general continuity equation in the form of operator. All right, again a general continuity equation. In operator form. Okay. Now, if a case is like this, if I say my case is steady as well as incompressible. If a case is steady, that means there is no change with respect to time in the density. So this term becomes 0. And if it is incompressible, that means this whole term is 0 in the equation. Okay. So from the case steady incompressible, previously I don't said anything about compressibility, didn't comment anything about that, but now I'm saying steady as well as incompressible. That means d rho by dt is 0. This implies from the above equation, I just only have, that implies my divergence of velocity will be 0 in such case for steady incompressible cases. And the case 4, just hold on. And if my case is unsteady incompressible, unsteady incompressible. So what do I say? That my, if incompressible is coming, then my total derivative of density will always be 0. So again, I see that my divergence of velocity is 0. So either it is steady or unsteady. If the flow is incompressible, my divergence of velocity is always going to be 0. Note. So we can say that if flow is incompressible, then divergence of my velocity will be 0. Okay. It doesn't matter that flow is steady or unsteady. Okay. It doesn't matter. Any doubts still here? Okay. So this was the continuity equation in Cartesian form. Okay. Now we will derive the continuity equation in polar coordinates. Okay, in the polar coordinates. Let's do that as well. Continuity equation in that is in the term of r, theta, and z. Okay. Suppose again, continuity equation again says that mass flow rate is nothing but mass in minus mass out is nothing but should be equal to mass stored. Suppose I have a fluid element. I again consider a fluid element like this. Okay, and something like this, and something like this. Okay, suppose it's like this, the fluid element in the form of a cylindrical format. Okay, so let us suppose I've made the enlarged view. Okay, so this is your center of that fluid. So let us suppose this is from this end to this end. It is making an angle of d theta, change in the angle. Okay. So mass enters in radial direction. So this is your radial direction, which has a radius r. Okay. So mass enters in through the radial direction. Suppose through here, mass flow rate in r direction. This fluid element has this much of dr. Okay. All right. And this is dz. Okay. So mass entered in the radial direction mr dot and exited. So I should not draw this here. Actually, I should draw somewhat like this. Mass entered in radial direction and exited like r plus dr. Okay. Again, we'll write the expression. Don't worry. Similarly, mass entered through the theta direction as well. So theta is your this direction. This is your theta direction, right? So here mass entered through here, mass flow rate in that theta direction, and mass exited through here. That is mass flow rate theta plus e theta. And again, mass entered through the z direction. Mass in z, mass exited through here, c plus dz. Okay, z plus e. Again, so how you will, so this was an elementary view. Okay, just take some few students have doubts that how it's, so just have a quick look, take a minute. I'll take a minute of break here, visualize it, then I'll write the derivation. Okay. Okay, I guess. So again, mass flow rate in minus mass flow rate out is your mass flow rate stored. So as we did in XYZ direction, similarly R theta and Z direction. So analogy is like that. So if it X, Y, oh sorry, it's not depending. So it's in X, Y, Z direction. Similarly for analogy in this is R theta and Z direction for the polar coordinates. Okay, so what do we write? Velocity in R direction is written as dr by dt. Velocity in theta direction is written as r d theta by dt. Total distance upon total time. So distance is nothing but this is your arc. This is your arc. Okay. I think some of you have not. This is your arc. So what is this? Theta into r. Theta is equal to L over r. So length of the arc is theta into. So that is I have written r d theta. And what is v of z? Dz by dt. V of z is nothing but dz by. Okay. So again we will write mass flow rate in minus mass flow rate out in r direction plus mass flow rate in minus mass flow rate out in theta direction plus mass flow rate in minus mass flow rate out in z direction is equal to mass flow rate stored. Again you will do, so your equation will something look like T of m r dot by dr dou r dr minus d of m theta dot by dou theta, that is r d theta d theta minus dou m z dou z dz is equal to dou m by dou t. We are considering unit volume of element overall. Okay. So again, if you put all the values and cancel it out, so your final expression I'm writing, final expression will look like dou by, instead of rho u will be nothing but rvr. Okay. I'm taking an analogy from the Cartesian coordinate equation, general equation, rho r vr by r to r. Okay. Plus rho v theta by r d theta plus dou of rho vz plus dou z is equal to, sorry, plus dou rho by dou t is equal to c. This is your final equation in Cartesian. Oh, sorry, polar form. General quantity equation in polar form. Okay, in polar form. All right. So if I want to write for the 2D incompressible flow case, like so incompressible means dou rho by dou t will be 0, and 2D means in x direction you will write, suppose through Cartesian coordinates you write dou v by dou y, okay, is equal to 0. So dou rho u by dou x, it is like that, but rho it goes to the right hand side, it's incompressible. So similarly in the polar coordinates will be dou r rvr dou v theta r d theta equal to 0. Okay. And what will be the streamline equation? Streamline equation. So it will nothing but for Cartesian, what was the streamline equation we did in the last tutorial? That is dx by u is equal to dy by v. So similarly, dx here will be dr or dr, and u is nothing but rvr. So this rr cancels. So I'll just write dr by vr is equal to dy is rd theta, rd theta by theta. This is your streamline equation as well. Okay, clear? Any doubts? No doubts? Okay. So let's come to the topic of acceleration of the fluid flow. Although we have started this thing in last tutorial of acceleration of fluid flow. Hold on, please. To charge. Put it on charge. Now let's come to acceleration. Acceleration of fluid flow. So we know that a fluid flow velocity is function of space and time. So acceleration is also function of space and time. Okay. So space component is known as a convective component and the time component is known as a local component. So if the direction of velocity changes, that means there is a, so acceleration will have eventually two components as like velocity. Okay, one tangential component, one radial component. So if the direction of velocity is changing, that means that is your centripetal or centrifugal acceleration, which is responsible for the change in the direction. But if the magnitude of acceleration is changing, that means tangential component is important. Okay, responsible for that. So we know that velocity v is function of x, y, z, and t. Okay, and we know that acceleration is nothing but total derivative of velocity. Okay, so we have written this equation in our previous tutorial that our acceleration, that is total derivative, is nothing but, what is the equation? V dot del of v plus dv by dt. This is our acceleration. Okay. So acceleration itself have, in Cartesian coordinates, we can say it has three components. So acceleration have a component in I direction, a y and j direction, and a z in k direction. Okay, in k direction. And net magnitude of acceleration can be written as a of x square plus a of y square plus a of z square. Okay, this is the magnitude. So how you will write the ax, this component ax? So a of x is nothing but du by dt, because velocity component in x direction is u. Okay, du by dt. A of y will be dv by dt, and a of z is dw by dt. dw by dt. All right. Suppose if the total velocity is a function of x, y, z, and t, that is space and time. So individual components will also be the function of the space and time, right? So let's say that my velocity u is a function of x, y, z, and so how will I write the acceleration of in the x direction? So first of all, how will I write the velocity u if it is a function of x, y, z, and t? So derivative of the velocity u can be written as d of u can be written as d of u dou of u by dou x dx plus dou of u by dou y dy plus dou of u by dou z dz plus dou u by dou t. Okay, and the acceleration will be a of x will be total derivative du by dt is nothing but dou u by dou x dx by dt plus dou u by dou y dy by dt plus dou u by dou z dz by dt plus dou u by dou t dt by dt. This cancels out. So this is nothing but your velocity components in each direction again, u, v, z, w. So you can write them u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t is your a of x. Okay, so it is scalar form in Cartesian coordinates, the acceleration. Similarly, how you will write for the y, u dou v by dou x v dv by dy w dv by dz dv by dt, and similarly you can write for the z direction as well. Okay, so these are your individual components. Now how you will write in the streamline form? Okay, now in the streamline form in the Cartesian coordinates. So this is scalar form in Cartesian. Scalar form in Cartesian coordinates. Okay, this is a scalar form. Now streamline form. Now the streamline in Cartesian. Okay. How you will write? So that means what is a streamline? We said that it's an imaginary line. If you draw a tangent on that curve, so it will give you a velocity vector. Okay, so suppose we have studied this thing in the last two. You have like this. This is your suppose your streamline. Okay, your streamline is like this only. Streamline. And some displacement has happened so far. Displacement S, and this is your d of S. So if you draw a tangent on this, that will give you a velocity vector, right? So your velocity vector is nothing but function of displacement, width, and time. Okay. So what will be the total velocity? dv by dt is nothing but dou v by dou s ds by dt, right? Plus dou v by dou t dt by dt. Okay. So dou s by dou t is nothing but your velocity, this component. This is v dv by ds plus this cancel out. This is dou v by dou t in the streamline form. This is your net acceleration. Okay. Got it? V dou v by dou s plus dou v by dou t in the direction of streamline. In the direction of streamline. Okay. S. S cap. So if my flow is 1D, one dimensional, for 1D flow, your displacement will be nothing but your x. So acceleration will be v dou v by dou x plus dou v by dou t. Okay, this is the acceleration. And similarly, this is the x direction acceleration only. Okay. So velocity vector has a magnitude as well as a direction. Okay. Since velocity is a scalar quantity, so it has magnitude plus direction. All right. It has magnitude plus direction. It depends on both of them. So suppose one of my streamline is like this. Okay, this is my streamline. A curve form, flow is flowing in a curve shape. Okay, curvilinear shape kind of thing. So this is your streamline, suppose. Okay, so if you draw a tangent on this curve now, okay, tangent at gave you a velocity vector v1, and at this position gave you a velocity vector v2. So that means a velocity is changing its direction as well as magnitude is also changing. Okay, magnitude is also changing. So how the magnitude is given and how, so for this, from the center of this, suppose this is the center of this streamline of the flow. Okay, wherever it is flowing. So it has a total acceleration which is sum of tangential plus radial component. Okay, because velocity is changing its magnitude as well as direction. So total acceleration will come into play. That is radial and tangential. So I will write a normal radial component, that is AR, that is your centripetal or centrifugal, you can say A normal, and this is your A tangential. Okay. So your total acceleration is nothing but the sum of tangential and normal. Okay. So normal A, you can say that direction, when the direction is changing, then the normal component plays a role. Vector which for component for magnitude change, tangential component is responsible. Okay. So you can write A of tangential is nothing but this is along the streamline. Tangential means along the streamline. Streamline is nothing but imaginary line. If you draw a tangent on that point on that curve, that gives you a velocity vector. So this was your velocity form in the form of streamline. That is v dv by ds plus dou v by dou t of streamline direction, and A normal is nothing but v square by r. You know the centrifugal acceleration from the mechanics. That is in the normal direction. So A total can be written as A tangential plus A normal, that is v dou v by dou s plus dou v by dou t s cap plus V square by R n cap. Okay, and this is your A total. Okay, total acceleration. And what will be the magnitude? A total magnitude will be some of A tangential square plus A normal square. Okay, square of. All right, clear. I think this is clear, pretty much clear. Any doubts still here? Okay, so we'll take a short break and then I'll join back. I think, hello, I'm audible now. Okay, I'll again share my screen. Just hold on. Okay, I think now it's visible. Okay, so I was talking about rotation in a fluid element. So omega angular velocity is nothing but change of angle d theta by dt. Okay, and net omega is nothing but from the right hand thumb rule. If it's flowing in an anti-clockwise direction, the direction will be upward. Flowing in the clockwise direction will be downward. So net in the z direction will be omega 1 minus omega. So I was saying a case that if my velocity u is only a function of y and velocity v is only a function of x. Okay, so this is a streamline. So let's draw velocity component. Net velocity is v vector, has two components u and v, small g and small v. Okay, so I'll consider a small element now of this. Let's suppose it's a axis, and I have a small element here, fluid element. This is my fluid element. Okay, so let me name it A, B, C, and D. A, B, C, D. Okay, so this dimension is dx of this element, and this dimension is dy. Okay, so there is my velocity u in the x direction, that is velocity u, and it is changing with y, not x. So in the y direction it will change, that is u plus dou u by dou y dy, right? And there is a velocity v in the y direction, and it is changing with x. So in the x direction it will be v plus dv by d by x dx. Okay, dv by dou v by dou x dx. All right, so this generally represents rotation. These components represent rotation of velocity u and v in x and y and x direction. So rotation of velocity u in y direction is this. Rotation of velocity v in x direction is this. Okay, so that means if there is a difference in the velocity, the fluid element is going to move. So fluid itself is something that is called as continuously deforming. When we defined in the first tutorial that difference between solid and fluid. Okay, so here what we can say, let me just drag it to here. Okay, so what we can say, this. So for both x and y direction, I'll frame. So first individual directions I'll frame. So again, my fluid element, I'll because of the difference in the velocity in the x direction, which is changing with y. So there will be a displacement in the fluid element. This, like this, okay, like this, which incorporates the shear stress formula. Okay, we have discussed this thing first tutorial. Okay, so that means there is some angular change in the velocity, that is the angular change in the fluid element, that is dou of beta. Let us suppose dou of theta. dou of beta. So this was your velocity u, and this is in the x direction. What will be this much amount of displacement? Okay, so your velocity u is remaining there. So the net displacement is velocity into time. So velocity, the change in velocity is dou u by dou y dy, and change in time is dt. Okay, so this is your displacement in the x direction. Remaining u remains same. Okay, so rotation of u has happened in the y direction. In the y direction, if you see, observe, the fluid element has rotated in the y direction, not in the x direction. So rotation of u in y direction okay. So how we can write it? Tan of d of beta can be written as, from the angle perpendicular is this and base is this. So what is the length of the fluid element in y direction? It is dy. So that is dou u by dou y dy dt by dy. So this cancels out. Okay. So dou, and for a small rotation, tan d beta can be written as d of beta by dt. From the right hand side, it can be written as dou u by dou y. Okay. And we can also write it as, suppose, omega 2 for this in the x direction. And it is in, if you observe, this is a clockwise rotation because of this. So a clockwise movement has happened, clockwise movement. Okay. So it is clockwise. So we assume that clockwise is negative or negative. Okay. Next, rotation of, because of the velocity v in the x direction. So let us again draw. This was my fluid element. Then this was my velocity v. Okay. So again, the fluid element has been displaced, this time in y direction. Okay. Sorry, x direction. Now the fluid element has been displaced from in the x direction. Okay. So what is the distance traveled? So again, shear stress will be this. Okay. And it will be a anti-clockwise rotation eventually. Okay. What is the amount of displacement has happened here? Dou v by dou x dx dt. Okay. This is your displacement. And let us suppose this angle is nothing but d alpha. Okay. This is how much in the x direction is the element length in the x direction is dx. So again, I'll write rotation of v in x. Should write like this. Rotation of v in this direction. Okay, so tan of d alpha is nothing but perpendicular dou v by dou x dx dt by dx. So this cancels out. So small rotation tan d alpha can be written as d alpha, and by dt from the right hand side, it is dv by dx, dou v by dou x. Okay, and let us suppose this is nothing but your omega 1, and it is in clockwise direction. Okay, so let us assume, sorry, it is in anti-clockwise direction. That was clockwise direction. It is in anti-clockwise direction. So we assume that it is positive. It is positive. So my net rotation will be what will be my net rotation? So as fluid is continuously deforming, okay, which is continuously deforming because of the rotation of u in y and v in x, okay, because of the rotation. So my net rotation, how will I write? So first of all, how will I write my mean? Omega z, as I said, from the log e is nothing but omega 1 plus of minus omega 2 by 2. This is your mean. Okay, so it is written as 1 by 2 omega 1 is dou u by dou x and dou u by dou y. Okay, this is your mean. Okay, dou u by dou x minus dou u by all, because half is this now, that's why this half is common. And omega 1 omega 2 I've written dou u by dou x minus dou u by dou y. Okay, so how my fluid element will look like in together? This we studied separately, one by one, in both x and y direction. So how my fluid element will look like? My final fluid element will look like something like this. It's a 2D fluid element. So originally my fluid element was like this, and now my fluid element look like somewhat like this. Okay, so that means there is shear stress in both this direction and this direction. Okay, there is dou beta by dou t change, continuous deformation is happening, and this is dou alpha by d alpha by dt. Okay, so this is your rotation. This is your omega 1, and this rotation is your omega 2. Clockwise is omega 2 and omega 1. Okay, and this is your final change in it. This is your change. How that is nothing but your, how will you write? Shear strain rate that has happened here. Shear strain rate, and it is because of dou b by dou t and dou alpha by dou t. Okay, dou b by dou t and dou alpha by dou t. How will you can write? This whole angle is 90. If you subtract this angle and this angle, you will get this. So this is nothing but pi by 2 minus dou alpha by dt minus, or I can write dou alpha dot, right? Pi by 2 minus d alpha dot d beta dot. Okay, this is a, okay. So my final shear strain rate, how it will be looking like? Gamma xy dot, or you use a symbol, some books use a symbol epsilon xy dot is nothing but dou v by dou x plus dou u by dou y. So this is your shear strain rate. Shear strain rate. This is your rate, shear strain rate. Okay. And what is shear strain rate tensor? Let me write that also. It is just half of that. You can see the derivations from the book as well. So epsilon xy dot is nothing but half of d alpha by dt plus d beta by dt. That is half of that to magnitude. Okay, dou v by dou x plus dou u by dou y, that is your xy dot, and that is nothing but called as shear strain rate tensor. Shear strain rate. So when tensor has been asked, it will be half of the shear strain. Okay, and we write omega, that is the net rotation, is nothing but half of curl of v. Curl operator you might have studied in the mathematics. That is half of grad cross. It is a cross product of curl is nothing but cross product of grad operator and the velocity vector. So how you solve the cross product? It's nothing but half of I j k dou by dou x, dou by dou y, dou by dou z, u v w. Okay, just do it. That is half of dou w by dou x minus dou v by dou z I cap plus half of dou u by dou z minus dou w by dou x j cap plus half of dou v by dou x minus dou u by dou y k cap. Okay, so these are your individual components. So net omega is omega xi cap plus omega yj cap plus omega z k cap. Okay, if I'm saying my flow is irrotational, for irrotational, my omega will be 0. That means my omega x, omega y, omega z all are equal to 0. Okay, so that means my half of curl of vector v is 0. Simple. Del cross v is 0. If I remove this half. Clear? Any doubts? Okay, I'll take a short break, then I'll join back. All right. So let's come to the concept of circulation. Okay. So circulation is defined for the rotationality of the whole loop, not for an individual particle. So if you have a set of particle, because we are dealing with a continuum scenario. So I'm talking about the rotationality of the whole loop. Okay. So it is nothing but a line integration of a tangential component of the velocity along the closed loop. Okay. It is a scalar quantity and it is independent of the slope of loop and only depends on the area. You will get to know when we design. All right. And as we said, that anti-clockwise is considered to be positive. So let me write. The topic is circulation. And it is represented through this symbol. It is the line integration of tangential component of velocity okay, along the closed loop. Okay, it is a scalar quantity. It is independent of the slope of the loop and depends on area. Okay, so let us say we have a streamline set of streamlines like this, and we define a closed loop inside it. Okay, we consider a closed loop which carries individual particles. Okay, let us suppose a small element dl in this. Okay, this is your small element. Okay, it will have a velocity vector along the streamline. Is this? This is the velocity vector along the streamline. But the component of the velocity vector which is tangential to this loop, not to the streamline. The component, the velocity vector which is tangential to the streamline is v vector, which I have drawn. But I want a tangent to the loop at this point. That will be the component of the velocity vector. That is nothing but your, if I say it is theta angle, so this is v cos of theta. Okay, v cos theta. So this how my whole loop will have the components. Okay. Okay, all the components v cos thetas. Okay, so my circulation is integration of tangential component of the velocity which is along the streamline, velocity or tangential component of the velocity of the streamline at the tangential at the closed loop. Okay, so it is a line integration of the tangential component of the velocity along the stream, along the loop. Okay, so that means my circulation is integral over the closed loop of the tangential component v cos theta dl. Okay, integrated. dl is a particle. So it can also be written as v dot dl. What is the dot product? V dl cos theta. V dot dl. Okay. Okay. This is a circulation. Okay. Now let us consider a fluid element in this, and let us suppose that closed loop is in the form of a swim. Okay. Again, let us take a set of streamline. Okay. Let us take a small fluid element like this, having dimension dx, dy. Okay. And this is from the closed loop. I'm taking out one fluid element. Okay. And I'm studying one fluid element. I'll study on one and then integral over whole. That will give me the complete circulation. Okay. So I'll zoom it, make a zoom view of this. So this was dx. This is dy. Again, I say A, B, C, D. Flow is like this. So my whole flow will be anti-clockwise right now. Okay. Along the loop. Okay. So I say the velocity u is this, as I draw in the previous topic, dou u by dou y dy. Okay. And velocity vector v changes dou v by dou x dx plus v. Okay. All right. So my whole circulation along this loop ABCD is nothing but circulation along AB plus circulation along BC plus circulation along CD plus circulation along DA. Okay. So AB, the velocity is u. Here the velocity is u. Here the velocity is v. Okay. So AB, velocity and displacement both are in the same direction. So my expression is v dot dl or v cos theta dl. So u cos theta dl. So that is u cos of 0. Both are in same direction. Dx is also in this direction and velocity u is also in the same direction. So angle is 0. Dx. Okay. For BC, my velocity is v plus dou v by dou x dx. Again, velocity and y direction both are in same. So cos 0 dy plus for CD, my velocity is in this direction, whereas my dx is in left side direction. So it will be cos 180. So it is u plus dou u by dou y dy cos 180 dx plus v, again both are in opposite direction, v plus dou v by dou x dx cos 180 into, okay, this is your net circulation. So cos 0 is 1, so it will be u dx plus v dy plus dou v by dou x dx dy plus, sorry, cos 180 is minus, so it will be minus u dx minus dou u by dou y dx dy minus v dy minus dou v by dou x dx dy. Okay, so this cancels out. This cancels out. You are left with dou v by dou x dx dy. Am I right? Have I missed any expression? Dx v dy dou v by dou x dou v by dou x dx dy dou u by dou y dx dy. Have I missed any expression here? So we have defined for the boundary of the loop, internal particles will take care of it. Okay, and I assume that my loop is of the square shape. Okay, so contains lot of fluid particles. Okay, so let me verify one by one. So this term I've written, this term, this term I've not, sorry. This term is this. 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 And this term is this. So yeah, all the terms are written. Correct. So we are left with dou v by dou x minus dou u by dou y dx dy, and that is my circulation of A, B, C, D. Okay, this is my net circulation. So this dx dy is nothing but the area for a 2D element. A, B, C, D is nothing but dou v by dou x minus dou u by dou y. This is your net circulation per unit area. Okay, so net circulation per unit area is also per unit area is nothing but for now I'm per unit. When I'm saying per unit area, that means I'm talking about an individual particle now for per unit area. So that means it is nothing but your called as vorticity. This is also called as vorticity, and this is vorticity. Okay, and vorticity is twice of omega rotation. Vorticity twice of rotation. And what is rotation? Curl of half of curl of v vector. So this cancel out. So vorticity is nothing but curl of vector v. Okay, curl of vector v. So as we know that from here, since this per unit area ABCD, ABCD, ABCD rotation, sorry, my bad. We know that without unit area, since we know that circulation ABCD is nothing but V dot DL. DS also you can say, what goes to S. Okay. So this is nothing but from this relation, it can also be written the dot product of this in the normal form. Phi dot n cap D. Okay. This can also be written like this. All right. Yeah. This is nothing but your expression for vorticity, rotation, circulation. So I'll write the expression for definition of vorticity here. So vorticity is nothing but it is circulation per unit area and it is twice of rotation. Direction of vorticity same is same as of rotation. Okay, and it is a mathematical measure of rotationality. Mathematical measure of rotationality. Okay, that's important. So if the flow is irrotational, shear stress may or may not be there, but circulation and vorticity will be there. Okay, if flow is irrotational. And ideal flow is always irrotational. So viscous and shear stress will be zero. So how you write the curl again is your curl of V is nothing but your vorticity, and it is nothing but I cap, J cap, K cap. Okay. So if fluid rotation have a half rotation left, okay, Okay, so rotation have a half, vorticity don't have a half. Always remember like this. So for a rotational flow, my vorticity or omega will non-zero. For irrotational flow, this is a rotational flow. Rotational omega will be non-zero as well as vorticity will be non-zero. For irrotational, my omega will be zero and vorticity will also be zero. Okay. Also, the circulation will be zero. And here circulation will be non-zero. Okay. Is it clear, the concept? All right. So I think we can end our session here and we'll talk about the potential and stream function in the next tutorial. So all my recordings will be available by a sheet provided by the NPTEL team through your email IDs, those who have registered. And there you can find the links of all the tutorial videos as well as the link of the Google Drive for the PDF notes. Those who are watching from directly from the YouTube. So each of the PDF is available in my Google Drive link, and that link is provided in each and every video description. Okay, for all the courses, not for this course. And my YouTube channel name is YouTube NPTEL with Varnit. Okay, this is my YouTube channel. All right, so I'll see you in the next session. Take care. Bye bye.